Now we are coming to the next topic in module 3, which is base classification method. Now for base classification method, you have to have a little bit knowledge of probability theory, which you have already learned in most of your lower classes in maths. You would have learned it. Now I put a video in along with the slides. You can go through it for just a rough 2-3 minutes on the rules of probability. Now, probability based classification method is a statistical classifier. Statistics are being probability. Statistical probability is used for base classification. It is a prediction. It predicts whether a given tuple belongs to a particular class, and that is done based on Bayes theorem. We will be just revising Bayes theorem. Now, naive Bayes classifier is found to be comparable. That is, the naive Bayes classification has got comparable performance with decision tree and some neural network classifiers. Not all neural network classifiers. Neural network classifiers are better than naive Bayes, and decision trees are also better than naive Bayes, but not too much difference is there for some standard data sets. Now, if you want high accuracy and speed, then you require large databases for naive Bayes classification. Now, it assumes that the attributes are independent. Okay. Now, it assumes that attributes are independent and classes are also conditionally independent. So, if we have dependent attributes and dependent classes, it is difficult to use naive Bayes classification. That is, the effect of an attribute value on a given class is independent of the values of the other attributes. So, the attributes are not dependent on each other. In that case, naive Bayes classification is good. And the computations are considered to be naive, simply because normally in real world applications we do not get independent attributes and independent classes. There will be some kind of dependence. If we are using naive Bayes classification, we are assuming that it is independent and the values will not be actually accurate. That is why it is called naive. Okay, now let's first look at what is Bayes theorem. Bayes theorem is conditional probability. We already know what conditional probability is. Now, P of H given X. H is the hypothesis and X is the precondition. Before, whatever value was there beforehand, that is the precondition. So, H is the hypothesis and X is the precondition. When we say probability of H given X, what we actually mean is, what is the probability of the hypothesis happening if the condition X has already happened, and that is called posterior probability. That is the probability of H after X happens. Okay, the probability that the tuple X belongs to a class C, given that we know the attribute descriptions of X. So, given that all the X tuples X belongs to a class C, given that we have the description of X. That is what we are going to find out using Bayes classification. Okay. So, an example is, let the customers described by the attributes age and income. So, if we have given X is equal to 35 and 40,000, H is, will the customer buy a computer? So, it is either yes or no. Okay. Customer will buy a computer. So, H is yes. So, when we find probability of H given X, what we are trying to find out is, what is the probability of a customer buying a computer if his age is 35 and his income is 40,000. Okay. In this, probability of H given X and probability of X given H are both posterior probabilities, and probability of H and probability of X are prior probabilities. This is just existent on the data. No previous occurrences or conditions are there for these two. And this is the normal probability which we normally calculate. This is conditional probability. Now, the Bayes theorem states that probability of H given X is equal to probability of X given H into probability of h divided by probability of x. Now how do we get this? We will do the derivation. Before we do the derivation, I need you to just this much go through this video. When I send the PPT to you, go through this video, you will get all the basic details that are required for the probability rules to study this naive Bayes classification. Okay, now what I require is dependent events, because we are looking at probability of an event occurring when something else has already occurred. Now look over here. In the case of a dependent event, what we are doing is picking out, supposing we have a bag and inside the bag we have got sweets. We want to pick out 2 sweets from the bag consecutively. Pick one and then pick another without replacement. Now normally when we study for maths, this can be picking out balls from a bag, or it can be picking coins from a bag, whatever. It can be anything without replacement. Now if we are starting without replacement, say that we have got 2 types of sweets, A and B. Okay, so the first, when we begin, let's say that we picked out one sweet. It can be A or it can be not A. So the first, the chances, probability of A or probability of not A. Okay, now let's expand probability of A. If we do not replace A, then the second sweet, whatever it might be, is the probability of a sweet B given that A is already picked out. Okay, or the probability of a sweet which is not B given that A is already picked out. So we have got, if A is already picked out, then with the second sweet can be B or it can be not B, but A is already picked out. Now if the first sweet was not A, then it can be B, not A, and probability of not B, not A. Okay, so all the probabilities are probability of B given A, probability of not B given A, probability of B not A, and probability of not B not A. Okay, now what we want to do is, what is the probability of A and B? That is the intersection of A and B. The probability of A and B is this direction, right? There is A as well as B. That's the only thing over here. So the probability of A and B is probability of A into probability of B given A. So that is given over here. The probability of A and B, or A intersection B, is equal to probability of A into probability of B given A. That means A is already picked out and then B is also being picked out. This is one rule which we need to remember when we are deriving the Bayes theorem. The rest of the things is just like if we want the probability of A and not B, then you have to follow this path. Not A and B, this path. Not A and not B is this path. So that is the rest of the formulas. Now this is what I need. Now let's look at the derivation of probability theorem. We already know for dependent events, not independent, for dependent events, one event occurring after the other occurs. We have got probability of A given B is equal to probability of A intersection B divided by probability of B. How did we get this? Look at this over here. Okay, probability of B given A is equal to the probability of A intersection B, and this will come down, divided by probability of the first event. So that's the same thing that's happening over here. Probability of A given B is equal to probability of A intersection B divided by the probability of B. Okay, similarly over here we have probability of B intersection A is equal to probability of B given A is equal to probability of B intersection A divided by probability of A. This is derived from this equation. Okay, so probability of B intersection A is equal to probability of A intersection B divided by probability A. Probability of A. Okay, so from this we have probability of A intersection B and probability of B intersection A is the same because two sets. So the intersection part is the same. So if this is the same, then probability of A intersection B into PB is equal to probability of B intersection A into PA. So that is given over here. Okay, so this is not divide, this is into P given A. If this is the case, then probability of B intersection A is equal to this divided by P of A, and this is the Bayes theorem. This is how the derivation is done. Okay, now let's go for naive-Bayes classifier. Once you know the naive-Bayes theorem, the Bayes theorem, then we can just apply it into the classification problem. Now pay attention. There is a data set D with n attributes. So the number of columns is the n attributes. So we have over here a data set D with 1, 2, 3, 4 attributes. This is the class. So it's not counted as the attribute. That's the hypothesis. So 1, 2, 3, 4 attributes are there in this particular data set. Okay, suppose there are m classes. So there are m distinct classes in D. For a tuple X, the classifier predicts that X belongs to the class Ci with highest posterity probability conditioned on X. That means what the classifier actually does, it finds probability of X given that the class is Ci for all the classes. So in our particular example, we have only two classes, yes and no, that the customer buys the computer, yes, or the customer does not buy the computer, no. So we will have C1 and C2. So what we will do to classify a particular X is, we will find the probability of X given yes and the probability of X given no. Whichever is greater, that is the class to which we will predict the X value. Okay, so what we are doing over here now, supposing X is not a single value, X has got n attributes. In our case, we have got 4 attributes. So what we need to find is, we need to find the probability of X with each one of these attributes and then multiply each of these values to give you, so the probability of X given S is the Bayes theorem. So find for each of the attributes and then multiply each of the probabilities to get the probability of X. So to find the complete probability of X given Ci, I will find the probability of the first attribute given Ci, find the probability of the second attribute given Ci, all the attributes given Ci, and multiply all the values to get the probability of X given one particular class. I'll do that for both the classes, yes and no, and whichever is greater, that is my answer. This is the Bayes classification theorem. Now we need to know one more thing. If the attribute is categorical, we have a categorical value, then in that case I have to find P of xk given Ci for each of the categories. So if I have age, I will have youth, middle-aged and senior. I have to find P xk given Ci for youth, for middle-aged and for senior. Now how do I do with that? Okay, supposing P probability of x of k of Ci is equal to number of tuples of Ci in D. So how many tuples? Look at the age attribute and look at how many of those tuples have got say yes. Having the value xk for ak, that means each value, having youth, then having middle-aged, then having senior. you have to find out. Then divide by the total number of tuples in Ci, the total number of S values in Ci. That is how you will get Pxk of Ci. So for youth, you have to find it separately. For the middle aged, you have to find it separately, and for senior, you have to find it separately and multiply the values to get the total value of that particular attribute. Now, if we have continuous values means it's numbers, then we use the Gaussian distribution. All you need to do is find the Gaussian distribution of x of that particular attribute, the mean value mu, and sigma, the standard deviation of that particular value. Okay, now you know how to find mean value and how to find standard deviation. Let's apply it into this particular formula and you will get the value of P of xk given Ci, G of xk, mu Ci, sigma Ci. Okay, and there is an example over here. This particular example, let x is equal to 35, 40,000. A1, that is, this is age and this is income. Let the class label or attribute be yes. Suppose age is a continuous valued attribute and we have already given that age is equal to, the mean value of age is 38 and the standard deviation is 12 for customers who buys a computer. So wherever it is yes, this is the mu and the sigma value. Okay, now using these values, simply substitute it into the Gaussian equation and then you will get 0.032. Okay, now okay, this is how the calculation is done. Okay, so this is what you have to do. P of 35 given yes. So all I am doing is substituting it into the value e raised to minus x minus mu the whole squared divided by 2. This is a Gaussian distribution function. Okay, is equal to 0. So I have the values square root of 2 pi sigma e raised to minus 35 minus 38 the whole squared divided by, sorry, sigma is 12 and 2 into 12 square, that is equal to 1 divided by 30.079 e raised to minus 9 divided by 288. This will be equal to 0.032. Okay, so the value is 0.032. All you need to do is substitute the values. Okay, for the value yes. Okay, now let's continue. Now it has become simple. Supposing I have this as my data and my question is classify x is equal to, this is one question similar like this. A question has come in the previous regular question paper. In your last year's regular question paper, there was a question similar to this. Okay, all you need to do is, this is the data that is given to you. This is D. Now the question is classify x is equal to, age is equal to youth, income is equal to medium, student is equal to yes, credit rating is equal to fair. Now what we need to do is find probability of C1 given x and probability of C2 given x. Now C1 is yes, there are only two classes, yes and no. So probability of yes given x and probability of no given x. Whichever is greater, that is our answer. So what are we going to do? First, we know already that to find this particular value C1 of x, the formula is given as base classification. So this is our base classification. We are supposed to find the probability of x given C1 into probability of C1 divided by probability of X. We have to find that for each attribute. For every attribute, we have to find probability of X given Ci. And then whatever is greater, that is our answer. Okay. So, we are going to do that now. We are going to find out, first find the probability of class 1 and the probability of class 2. Okay. So, we have the probability of class 1 is equal to 9 out of 14, which is equal to, we have already done this earlier. So, look, we have got 9 yeses and we have got 5 no's. So, the probability of yes is 0.643 and the probability of no is 0.357 out of 14. Okay. Then we find out for age. We have already been given that the age is youth, income is medium, student is yes, and credit rating is fair. So, only with these 4 values, we are going to find the probabilities. So, probability of age is equal to youth, Bayes computer is yes. We have how many? Out of the yeses, how many have got age youth? That is what we are going to look. So, we know over here 9 yeses are there. Out of the 9 yeses, we have got, here there is a yes, 1 youth, and here there is a yes, 2nd youth. All these are not youth. So, out of 9, only 2 are youth. So, the probability of youth given yes is 2 out of 9. Similarly, find for no, that is 3 out of 5. Out of the 5 no's, 3 are youth. So, the probability we have got. Similarly, find for medium, income medium and Bayes computer yes, income medium, Bayes computer no. That is 4 out of 9 and 2 out of 5. Student yes, Bayes computer yes, student yes, Bayes computer no. Credit rating fair, Bayes computer yes, credit rating fair, Bayes computer no. So, now we have all the values which are required. Okay. Now, we substitute those values inside the equation for class. That is, probability of X given Bayes computer yes is equal to probability of age is equal to youth, Bayes computer yes, into probability of, because X has got 4 attributes. So, each of those attributes, then the value is yes. We have got already the values over here. Just multiply those values and we get the answer of the probability of X given yes. Okay. Similarly, we will find out the probability of X given no. That is equal to 0.019. Same thing. We are doing the same thing. Now, we look at to find the class Ci that maximizes probability of X given Ci, probability of Ci, because this is our Gaussian equation. We are supposed to find out, see, if you look at the equation, we are supposed to find out probability of class given X. Here, we are supposed to find out probability of the class given X. So, to find out the probability of the class given X, we have to maximize probability of X given Ci into probability of Ci. So, this is what we have to maximize. Since P of X is common, that we are not looking at. If we maximize the numerator, automatically the value will be greater. So, this is what we are looking at, the numerator of probability of class I given X. So, when we do this, we have already got the value of probability of X given class. So, that multiplied by the probability of each class, and then whichever is higher, that is our class. Okay. So, over here, the probability of X, to find out for yes, what we are doing is probability of X given yes into probability of yes. We already know the probability of yes. We've got the values. So, just multiply those values. So, we found out over here the probability of X given yes is 0.044 and the probability of yes is 0.643. So, multiply these two values. When you multiply these two values, you get 0.028. Similarly, multiply this value with the probability of no and you get 0.007, which is greater. The yes class is greater. So the naive Bayes classifier predicts for this particular set of values, that is age is equal to youth, income is equal to medium, student yes, and credit rating fair. For that particular set of values, the naive Bayes classifier predicts that the customer buys computer is equal to yes. This is how we do classification using naive Bayes classifier. It's very simple. You need to know your formulas correctly and just do simple mathematics. It is a multiplication and division mathematics. Okay, now there's one more thing that we need to do before we conclude. Laplacian correction. Now what will happen if for a particular value in my database there is nothing, okay, it is 0, we have 0 number of classes for a particular set of value in my database. For example, for middle-aged, we had 0 number of no's. You remember, we had 0 number of no's. So if we have 0, the probability value will be equal to 0. It will null all the values. So when you multiply, you will get all the values null. Okay, so this is a problem. To avoid this, what we do is, we can assume that our training database D is so large that adding 1 to each count. So if I actually have only 0, I'm going to do +1 to all of the classes. In that case, it will be a negligible, when we do the probability, it will be a negligible value, it will be some 0 point something 000. Okay, so this is the method. This is called Laplacian correction. Now we are going to look at examples so that you can understand it better. Okay, example, suppose that for the class buys computer is equal to yes in some training database D containing 1000 tuples. Okay, so the whole database has got 1000 tuple, but for the class buys computer is equal to yes, we have 0 tuples with income low. So for the value of income is equal to low, there is no yeses at all. There are 990 tuples with income medium and there are 10 tuples with income high. Okay, so there is nothing for the value income is equal to low. So what happens to the probability? Probability of the event of income being low will be equal to, that is, income is low and buys computer is equal to yes, will be equal to 0 because there is nothing there. Okay, so it is 0 out of 1000. This will be 9990 out of 1000 for income is equal to medium, and for income is equal to high, it will be 0.10. Okay, but if we are, now if this is 0, it will just remove all the values for low and the whole thing will become equal to 0, which is not actually correct. So in order to avoid this particular error, what Laplacian correction does is that it simply adds 1 to each of these values. So in income low, instead of 0, it will make 1. In 990, it will become 991. And instead of 10 tuples for high, it will be 11. So totally 3 tuples have been added to the total database. So it's not 1000 tuples, it's 1003 tuples. And the Laplacian correction, now the probability of income is equal to low and yes is 0.001. It's no longer 0. And for instead of 0.990, it has become 0.988, which is very similar to 990. Okay, and instead of 0.10, it has become 0.011 for income is equal to high. These values will be used to calculate the Bayesian values. That will be a better, give us better results than giving 0 for income is equal to low. Okay, this is Laplacian correction. With this, we are finishing module 3.